conceptual and the kind of the model about the future of jet quenching program at RHIC.
Okay. So well, it's a pleasure to be here. I think that's my 7th or 8th trip to ECT STAR, and I think it was really one of the most pleasant ones, not just because we had a lot of good discussion, but also because it was nice to see everybody again. The only complaint I have, and if I knew how to move forward, only complaint I have to the organizers, who I in general want to thank very much, is I could have done with a somewhat more dramatic title that I think would have been fitting, given the heroic effort that the collaboration here at Phoenix has been putting in over the last years in extraordinary times in assembling this detector. This is a picture that was taken about a week and a half ago after the installation of the inner hadronic calorimeter here. So by now we have the outer hadronic calorimeter, the magnet, and the inner hadronic calorimeter assembled there. So that also indicates the direction I want to take with the talk. I will not talk so much about how we are going to solve, once we have the data, all the important problems in the field, but I will show how we are going to use S-Phoenix and the upgraded STAR detector to get data that are really far beyond what we got from RHIC in the previous years. It's actually 22 years since the first collisions happened at RHIC. First collisions were 12th of June 2000. This picture, I believe, was taken on the 13th of June, when some of the experiments showed the first results that they obtained overnight. I think this picture raises a few important questions. So what is that thing? I don't know. Have I been wearing the same clothes for the last 22 years? I don't know. And also importantly, why do we think that in the remaining 3 years, we'll be able to do all the things that we haven't been able to do in the prior almost quarter of a century? And so that's what I try to explain from a sort of experimental point of view. What are the new tools that we're going to have, and what will they give us to allow us to do wonderful things over the next 3 years? So I see that the balance in the audience has shifted a bit towards the experimentalists over the last day. So to some extent, I'm of course preaching to the choir here, but such is life. So the overall goal, of course, and this is my go-to slide. I can't remember how often I've shown that since 2015. But the goal is to complete the RHIC science mission in the next 3 years. This was, of course, from 2015. So the first part of that completion of the science mission was done. Mapping of the QCD phase diagram with STAR, the beam energy scan 2. And now we get to the second part, which is to probe the inner workings of QGP by resolving its properties at shorter and shorter length scales. And there we rely on the complementarity of LHC and RHIC, as well as improved instrumentation at RHIC, including a new detector, which is called S-Phoenix. Usually we talk about the 4 pillars of the S-Phoenix science program, and more generally the science program at RHIC over the next years. But today, of course, I'll mostly focus on what is going to be new and how is the new stuff going to come about for jet correlations, jet substructure, and parton energy loss measured with heavy flavor. I think it's this workshop was further evidence that these goals that were laid out not quite a decade ago really remain important and under intense debate. So I think that's good to see. So how are we going to do that? If you think about this from an experimentalist point of view, I think this is a 3-step program. There will be significant improvements to the machine, RHIC, and then the 2 experiments, STAR and S-Phoenix, will really provide significantly improved performance compared to what had been done before. And overall, that will really make us stronger. I don't know if there are any Daft Punk fans in the audience, but okay. So first of all, RHIC. As you can see from this table, RHIC has been running for a long time. But if you look here at the 2023 and 2025 columns, which have the gold performance for those runs, you see that if you add those up, the integrated luminosity that you will get with a sufficiently long run, 28 weeks or so, will match or surpass the grand total of what has been collected in the last 20 years. So the first ingredient is really a significant improvement in the available statistics. And from an experimentalist point of view, it's of course much more valuable to collect this huge amount of statistics with a consistent detector configuration in a single run, rather than have to cobble together many runs where the detectors are not quite the same, either because of planned upgrades or because of some degradation. So that's the first ingredient. One has to notice, however, and that's to people who have mostly worked at the LHC, maybe not quite at the front of their mind. Most of the collisions at RHIC, when it's running at full blast, occur outside of so what one would prefer to have as the vertex range. So the diamond at RHIC is like this wide, where, for example, the S-Phoenix silicon vertex detector is this big. So only about 40% of the collisions happen in the region that we would like to have. There's one innovation that we will try with next year's run. We will run the gold beam with a crossing angle where, well, if you take the beams, you tilt them a bit to each other, you reduce the size of the diamond. You also reduce the luminosity overall by a large factor. However, the luminosity in the region that we're interested in, plus minus 10 centimeter around the nominal vertex, will not be affected that much. So that's two things to take away from that slide. The third thing is, just as a ballpark number, the maximum collision rate that you can get is at RHIC for gold is 150 kilohertz, maybe a little more, which is in the same ballpark of what LHC could provide for lead if they really push it, maybe 100 kilohertz or so. But this number is good to keep in mind for a few minutes, because you have to match it to what the experiments can do. So I've been mentioning 3 years of running a number of times. You can ask later what the prospects are for running more than 3 years, but that is the current plan, 3 years. And then if you think about if your basic constraint is that you want to do useful science with S-Phoenix, there's actually not much freedom in how to use these 3 years. You have to spend 1 year commissioning the whole setup and taking some first gold data. You have to spend 1 year taking as much PP reference data as you can reasonably get, and maybe some P gold. And then you have spent 1 year just running gold at the top energy flat out to get the largest possible data set. And that is the RHIC run plan. Star has a slightly different opinion for run 24, but in the end, I think necessity for the S-Phoenix program will dictate how this is going to be done. For those who like to think in the inverse nanobahn, if you add up the sample luminosity, you get on the order of 30 inverse nanobahn, recorded about 20 for lead, for gold, sorry. Challenge at RHIC, something that, well, it's not very difficult to figure out, but if you haven't thought about that, there is a little bit of there's a different situation at RHIC than at the LHC. At LHC, the part-on luminosity is maximal if you run PP at 10 to the 34 luminosity. At RHIC, however, in particular, if you look at, I mean, you can look at either way, but if you look at 10 centimeter vertex selection, the number of binary collisions that you get per second is about an order of magnitude smaller in pp than in gold. And that comes to something that we have discussed a couple of times or mentioned a couple of times this week. At RHIC, it's really a challenge for rare probes to collect sufficient statistics in pp. So even with a perfect detector, well, you cannot collect more collisions in pp than the machine provides. Of course, for some probes, jet quenching helps a bit. I mean, if the jet yield in gold or the hadron yield in gold gets suppressed by a factor of 5, you get closer to a matched situation between pp and gold. But for the photons, which are unsuppressed, it's really going to be difficult to collect as much pp reference data as we would like. The other very challenging situation, and I'll come back to that later, is if you look at soft probes that you cannot trigger on. At that point, you become, in terms of the luminosity that you look at, limited by the event rate that the detectors can take. And for a fixed event rate, gold wins by the average number of participants per collision, so by 2 orders of magnitude. So for untriggered probes, collecting enough statistics in pp is an even bigger challenge, in particular if those probes are rare, like heavy flavor. Okay, and I will come back to that point later. So now I'm going to talk a little bit about the 2 experiments plans and what these plans are going to buy us. And this is all based on the recent BMUS proposals from SPhoenix and from STAR. So the links, if you want to know all the details, you can look at the links. Let's first have a quick look at STAR. Of course, one of the big items, the big efforts in STAR over the last years was the forward upgrade, which was implemented and successfully run in run 22, which ended 7 weeks ago. Covers forward rapidity with tracking and calorimetry. It will see obviously its first use in gold in 23 and 25. There are many opportunities there, which I, however, will not discuss because it's mostly at low PT, in particular on the tracking side, because you just don't get a lot of bending power with a forward detector from the solenoidal magnet. And forward jets in gold, I think, are going to be a challenge. I don't know if Peter can correct me there. Okay. However, one shouldn't forget that STAR in the previous years made major upgrades for the beam energy scanning, including the upgrade of the inner TPC, which increased the rapidity acceptance by 50%, and also implemented the event plane detector, much better event plane resolution, the forward TOF. All of that will come in very handy over the next 3 years. But one of the major upgrades that I only learned about a few weeks ago is an upgrade of the TPC readout by about a factor 2 to 2.5 to 5 kilohertz to 5 kilohertz readout rate from the about 2 kilohertz or less that we had before. I was very surprised when I heard that number because so this is an experimentalist equivalent of a slide full of 3-line equations. So STAR is a traditional TPC with a gating grid, which only opens the amplification stage to the incoming charge once there was a trigger. That prevents the ions that you create in the amplification from flowing back into the chamber and creating a lot of space charge there, which distorts the path of the incoming electrons, which of course carry the position information about the track. So you open this gating grid when you want to read out the event. And well, typically you in ALICE and STAR so far, that was done at the rate of 1 kilohertz. Now this is going to be increased to 5 kilohertz in STAR, and I know that the gating grid driver has already been tested, but this is really, I think, going to be a very interesting challenge to make sure that you will keep control over the space charge distortions in this case. So I really look forward to seeing how STAR handles that. But if everything works, what you will get is much larger data sets than in the previous runs, like I mean, factors of 1.5 to factors 10, depending on how you allocate the available bandwidth, compared to run 14 and 16. Still, the event rate, even at 5 kilohertz, remains small compared to the collision rate for gold, and in particular for PP, where you have collision rates of a couple of megahertz. And therefore, it's important that the star will be able to select photons sampling from a wide vertex range, because they will not use a crossing angle. And then also jets with an EMCAL-based trigger. Of course, as we have been discussing for many years now, how exactly to understand these hardcore EMCAL triggered jets is interesting. Here, STAR has a sort of summary of the benefits of this program and the goals for this next 3 years. And the increased statistics will really allow to close or at least narrow the gap to the kinematic reach covered by the LHC, and provide, I mean, obviously significant improvements versus the existing measurements. There are also major benefits for Quarkonia, but for those of you who don't follow things that closely, STAR at the moment will not have a microvertex detector. So for open heavy flavor, you would have to rely on single electrons, which is not my favorite way of accessing open heavy flavor. Here's the sort of couple of plots from the BMUS proposal. I'm showing existing measurements and how the reduced uncertainties will help there. This photon jet, as I said, there, particular for photons, it will be a challenge to collect sufficient statistics for the PP reference, because the rate of photons just is an order of magnitude lower than in gold. Okay. So now let me talk about S-Phoenix a bit. This is an engineering drawing of how the detector will look like in the interaction region. As I said, a lot of the pieces have already been assembled. I disagree on the timing with Konrad there, but we can sort it out later. This is the structure of the detector. It's some of my colleagues in S-Phoenix don't like it when I say that, but it's a fairly conventional collider detector with a solenoidal superconducting magnet, 1.4 Tesla. We inherited that from Babar, hadronic calorimeter on the outside. Next step in after the magnet, an inner hadronic calorimeter and electromagnetic calorimeter, and then a tracking detector with a large volume tracker for getting the momentum, and a microvertex detector to identify heavy flavor decays, and the primary vertex. So a fairly conventional setup. The inner part of this detector, if that reminds you of Alice, but miniaturized by a factor of 3, then that would show that you paid attention. Where do we stand? I really like this slide. About here, so we have installed the inner HCAL. EMCAL is next. The shield wall is open, and we're assembling everything on the carriage platform, which will then be rolled into the interaction region. At which point we'll map the magnets sometime in the fall of this year, and then install the tracking detectors, and then everything will be closed up on February 22nd, 2023, and then we'll start data taking. For the experimentalists among you, it's obvious that this is somewhere between ambitious and unheard of, because the time for commissioning the detector and making sure that all the cables go where they're supposed to go, etc., is really extremely tight. But this is the schedule, and we'll stick to the schedule or die trying. This is the plan. Although not everything always goes according to plan. For example, one thing we didn't have in our RHIC registry is the UPS facility where our beam pipe is in transit catching fire, and our beam pipe burning down in the back of one of those UPS trucks. That happened 2 months ago. Fortunately, STAR has a spare beam pipe from the heavy flavor tracker days, which actually fits perfectly. So we're going to use that. We're not going to ship it with UPS anywhere, and that was narrow escape there. The other thing, okay, it's not funny, but we are victims of the neon shortage, like the semiconductor industry, because most of the neon that you could buy cheaply came from the Ukraine, made out of byproducts from Russian steel production. So that avenue is closed. Of course, we were planning to use neon CF4 in our TPC. We found out that an argon CF4 mix is maybe not quite as good, but definitely workable. So we'll see how many more stumbling blocks we encounter in the next months. But the plan is to have first collisions on what Ash Wednesday 2023, marked in my calendar. You should mark that in your calendars as well. Okay, so what will S-Phoenix buy us? So, well, one major change compared to what was available at RHIC so far is the hadronic calorimeter. We have a hadronic and electromagnetic calorimetry covering, of course, 2 pi in azimuth, a pseudo rapidity of about 1.1, and a 15 kilohertz maximal readout rate. That is essentially constrained by funding. It's the throughput of the electronics. If you could buy more electronics, we could increase that, but that is what the funding that we had now buys us. It's actually store averaged, and with the crossing angle, it's just a little bit lower than the collision rate, the average collision rate. It's the first mid-rapidity hadronic calorimeter at RHIC, and on the next couple of slides, I will show some of the things that buys you. Following the discussion that we had during this week, I mean, one important aspect is that we'll be able to do, in combination with the tracker, both particle flow jets, calorimeter only jets, and drag jets to really beat them against each other and compare to various experiments. The hadronic calorimeter buys you an unbiased jet trigger in PP. Thank you. Well, that obviously goes some way of alleviating the PP reference statistics shortage, and will allow us to do RIA with a real PP reference out to about 70 GeV for central gold. Then the tracker, continuous readout TPC. I put a couple of plots there because Jin Young asked earlier in the week whether we had any tracking, and yes, we do. And not only do we have tracking, it is in terms of momentum resolution a big step forward compared to what we had previously at RHIC. Our larger magnetic field mostly compensates for the shorter track length that we see in our TPC compared to STAR, and then our better single point resolution gives us a better momentum resolution, provided we manage to correct the space charge distortions to a level of about 150 micron from initial distortion of a little more than 1 millimeter on average. Also very good tracking efficiency out to high PT. We're still working to improve things at a lower PT. One thing that I want to mention again for the theorists, maybe not that obvious, measuring single hadron spectra out to very high PT is not trivial, because at that point you're looking at, let's say, the 100 most highest PT tracks out of 1 trillion. So you have to make sure that whatever your detector does and whatever your software does doesn't go haywire at the rate of a few in 1 trillion. If you do that wrong, you wouldn't be the first one. This is a published CDF measurement, and you don't often see a HEP measurement get things wrong by a factor of 1,000. Here, the hadronic calorimeter really helps because you can reduce the number of events by requiring a jet. You reduce the number of events in which you actually search for tracks, and that correspondingly reduces the background. This is what Atlas and CMS have used to get to the highest PT in charge hadron spectra at the LHC. So we will be able to get out to about 50 GeV. And then, of course, we can do a lot of the usual jet measurements. I actually don't think I have to go through this in detail. So we should be able to, with good statistics in the range up to 50 GeV or so, essentially do all the measurements that were discussed this week: photon jet PT balance, subjets in all the various forms, jet V2 with high statistical precision, and I think it will be interesting to see what this plot looks like in 3 or 4 years from now. I think it's hard to predict. I don't know exactly what I'm expecting there. So the full complement of jet measurements will be possible. And then, of course, we have this microvertex detector, essentially a copy of the Alice ITS in a barrel. Same chips, same electronics, slightly different mechanical layout. A significant step forward from the STAR HFT, which really pioneered this technology in heavy ion collisions. But we have 3 layers. The detector is bigger, it's closer to the beam pipe, and has much faster readout now. And this enables really a full heavy flavor program at RHIC, including for the first time B-jets. Then there's one more thing. Okay, I think I should probably skip the details there. But again, to address the problem of PP versus gold-gold statistics, one clever thing that one can do is use a hybrid readout where you have 15 kilohertz triggered calorimeter events, but a streaming readout of the tracker events. I'm not going to explain exactly how that works. It's not difficult, but this allows you to collect, for example, 10% of all events in PP, which compared to previous efforts where you read out at, say, 1 kilohertz or 2 kilohertz rate, gives you a factor of 100 in statistics for heavy flavor measurements. So that's a huge step forward and will really, for the first time, allow measurements compared to a precise PP reference over a wide kinematic range for heavy flavor. For example, from the D0 and B to D0 decays, you see the uncertainties are the statistical projected uncertainties, including the detector resolution and selection efficiency, are tiny. You can measure DV2 precisely. And we can, for the first time, use the technology that was first developed by CMS for tagging heavy flavor jets at RHIC. This is, I think, more challenging than these plots make it look, but we are confident that we will be able to do quite well there. So that was the overview. Here's a kind of summary. So in case you have a minute to spare from looking at your email, what I think you should remember is that we'll start in February 23, run for 3 years, gold-gold, PP reference, gold-gold. The increased RHIC luminosity and the STAR and SVIN's readout performance will give a significant order of magnitude to 2 orders of magnitude increase in the available event statistics, and will allow us to really connect to the LHC directly. And the new instrumentation, like, for example, the SVIN HCAL and the NVTX, will also allow us to perform measurements from different angles and really reduce the systematic uncertainties. So that's good. This is sort of a plot that I showed in the 2014 Hot QCD town meeting that preceded the long-range plan. Actually, this is comes back to the discussion about machine learning. This is what some machine learning model thinks this plot would look like if it had been painted by Claude Monet. But the point here is that tomorrow is finally around the corner, and I think that is something we all should look forward to. And I'll just leave the very nice summary that the PAC, the RHIC PAC, has provided in the last year up here. Thank you.
Thanks a lot, Gunther, for an exciting talk about futures.
I left 1 minute for questions. So.
Yeah, no, we have time. So, Peter, you started off.
Yeah, I have a question about this intersection diamond, and I said the MVTX is what it is. And for heavy flavor measurements, you have to constrain your vertex. But But I wonder whether you considered whether you can use the kind of out of MBTX acceptance for other channels. Let's take Photon Jet as an example.
Mm.
You know, if you don't require the vertexing and you know with reasonable precision what your material is, all the surfaces and so on for hard probes, you may be able to suffer the presence of some material and use the out of vertex out of the center vertices. That would really increase your luminosity by a lot, as you showed.
Yep.
Have you considered that?
We have thought about that. We have agonized about that for a long time. The limiting factor is not the extra material, but the fact that the distortions in the TPC are proportional to the overall space charge, which is proportional to the collision rate. So with the 150 kilohertz collision rate, we put 2.5 times as much space charge in the TPC as with the crossing angle. And we will certainly try to find out whether we can live with that. And if we can, then we can relax that and, for example, collect much better photon jet or calorimeter only measurements. But for the first run, we have to be conservative and make sure that with the conditions that we think should work, we have everything under control. If we are confident for the run 24 and 25, we'll certainly tell RHIC to really crank it up. Yeah.
So maybe I can ask you, it's a very stupid naive question from Matthias. So I didn't really understand this 3-run schedule. Is that something very, very fixed? I saw on your last slide, there was kind of a hope for something more, but you focused very clearly on like these 3 years, just to understand. Is that kind of
so if you start try to start a discussion about additional running after these 3 years, for example, in the program advisory committee meeting or with RHIC management or with POE, you at the moment you just get ignored. This is not Peter is actually more optimistic than me, surprisingly, but I don't know. Reality will tell whether additional running will be possible. At the moment, this is the plan. And
but why is there the EIC already starts?
Okay, so initially this is really constrained by the technical schedule for the EIC. If we want to start in 2031, you have to take over the accelerator right after the 25 run. Now, of course, the LHC schedule has slipped a bit. CD4 is now in 34. But that brings in the second constraint to build the EIC with the 1.7 to 2.8 billion price tag. You have to accumulate a large fraction of the US nuclear physics budget over many years. And that is the second constraint that you're facing if you want to continue running. Now, and then you have to get into detailed accounting questions where it depends on whether you're buying or selling. We'll see how that sorts itself out.
Thanks.
Thanks for the nice talk. I have another question kind of about this running plan. In many of our measurements, the systematic uncertainties from the modeling of the detector are quite important. And in the end, we're usually taking ratios or differences of AA to PP. Yeah. And so the prospect to be able to cancel out systematic uncertainties between the two collision systems can be very important. I don't know how much this has been thought about or studied by people, but it seems to do this, you need to understand how much your detector conditions are changing as a function of time. Yeah. And so here I see, I mean, at the LHC, this is very difficult to do because we have this 1 month period. But here, at least in this plan, it's 1 year of PP, the next year, gold. Has it been thought about whether to study perhaps mixing those and switching the systems in order to try to
like for the crossing angle, we have been agonizing over that for a long time. The problem is that this is all very constrained. If we could look forward to 10 years of running, I think it would be much better to switch every year and suffer the 2-week setup period that would incur. I mean, that's if I recall correctly, the advice from RHIC that you get, you lose 2 weeks. In this very compressed schedule, this is not something that you can easily afford. The other thing is, I think the natural thought might be, let's start commissioning with PP, and that's easier. I mean, a few tracks. less stage charge, we make sure it works in PP, and then we go to gold. But with a 3-year schedule, you have to start with gold, because if you find that something doesn't work, and you find that out in year 2 in gold, you're screwed. So you essentially have to start with gold. First half of the run is going to be just basic commissioning of the detectors until you can run everything at the full rate. And then you have half the year to collect the first gold data set, and that just in that half of the running period, there isn't enough time to switch to the penalty you would get from switching a species would be too large compared to the overall statistics that you can hope to connect. So it's a very good thought, and if there was less constraints, that's what we would do. But in 3 years, there's no choice.
Let's talk to Biden about this.
A very nice talk. This is more out of interest, but you emphasized very much the increase in luminosity for gold. So is that an improvement in the accelerator, some cooling or so, or is it?
That's a very good question. I should have anticipated, but didn't. I can send you the link to the document. We can look at the document together from which I extracted the tables. I don't know exactly what the underlying improvements in the machine are that enable that compared to 2016. But yeah.
Okay, I think we should close the discussion. Thanks a lot, Gunther, again.
Thank you.